couple of misprints in the exercises. One of them is small. So in the last exercise, of course, the integral is over the boundary, so over the circle, not over the disk. Now, there's another big issue. In problem 1, number C, the equation is wrong. And the correct equation, so thank you guys for those who told me about it. Indeed, it's quite clear that the equation cannot be correct. But since it happened, of course I'll update the exercise, but right now I'll spend some time giving hints to exercise 1, because probably you feel...
Just a question for the exercise you mentioned. First, the n, the power of the set minus 0, is that natural number or an e?
Wait a second. What are we talking about? The
Third exercise.
third exercise? Yeah. So it's a natural number. Yes. Yes. I forgot. Like this, right? Right. So there'll be a long extended hint to exercise 1 about so let's discuss the topic in detail. So let's start from some algebra. So let's talk about root of unity in complex number. So just by definition, let's say omega is a root of unity of degree n if, well, omega to the n equals 1, or equivalently, omega is a root of the polynomial z to the n minus 1. So a few remarks which will be used to some extent. So if omega 1 and omega 2 are roots of 1 of degree n, then their product, of course, is also such a root of unity of degree n. Indeed, omega 1, omega 2 to the power n is omega 1 to the n, omega 2 to the n is 1. So in particular, if omega is a root of 1 of degree n, then every power omega to the power k is also root of 1 of degree n. So all this is completely obvious. Now the picture of complex plane is the one you probably know. So we are considering a unit circle. And then the angle 2 pi over n. And so this point is cosine of 2 pi over n plus I sine of 2 pi over n. So it's what's called primitive root of 1 of degree n, meaning that any other root of 1 of degree n is of the form cosine of 2 pi k over n plus I sine 2 pi k over n. So this is like maybe denote this one by psi. So this is psi to the power k. Okay, so this is like standard, and maybe you knew this already in high school. So one important observation, which actually gets us closer to the problem. If omega is root of 1 of degree n, it follows that 1 plus omega plus so on plus omega to the power n minus 1 equals to 0. You know this? So the reason is, so you consider z to the n minus 1, and we used it a couple of times. There's a decomposition, z minus 1 times this polynomial. Alright, so omega is a root of left-hand side, and omega doesn't equal 1, otherwise it's not interesting. Yeah, omega different from 1. Of course, 1 is a root of 1. It follows that this factor, z to n minus 1 plus so on plus z plus 1, evaluated at omega equals to 0. But this is exactly 1 plus omega plus omega n minus 1 equals 0. Okay, now we'll use it for something. So we're getting closer to actual problem. So consider a function e to the power omega z, where omega is nth root of 1. Okay. So, example, which is a hint. Take n equal to 2. Then functions I'm talking about are e to the z and e to minus z. Okay. So let's differentiate this function. This will be omega e to omega z, of course. Let's differentiate it k times. And then, of course, this will be omega to the k e to omega z. Very good. It means that if we differentiate this function, how many? n times. Then this will be omega to the power n, e to omega z, but this equals to 1. So this is e to omega z. So for any nth root of 1 omega. So this is important, and believe me, this will be used in exercise 1b and c to be corrected. One more thing, which is important and which actually will be discussed a bit later. So let's take all these, so take all roots of 1 of degree n. Non-trivial. All non-trivial. So we're not counting 1. So we know what they are. So you take primitive root of 1, so the generator, and then you apply. So psi is cosine 2 pi over n plus I sine 2 pi over n. Then these elements are, so we take psi squared, so on, up to, I'll take 1 as well. So take 1, psi squared, and up to the last one. Psi n minus 1. So these are all roots of 1 of degree n. Then let's take corresponding functions of the type I described. So e to 1 z, so I'll just write e to the z. Then e to psi z, e to psi squared z, up to the very end, so e to psi n minus 1 z. Now let's take the product. So starting from here, you may think that this is a hint. Let's take the product. E to the z times e to psi z times so on times e to psi to n minus 1 z equals to e to, well, the sum of these, and the sum of these is 1 plus psi plus so on plus psi to n minus 1 z. But this sum equals to 0. So this equals to 1. So the product of all such functions equals to 1. Now let's consider. So like toy version of problem 1. Let's consider hyperbolic sine and hyperbolic cosine. Right? So these are also power series, but they are related to number 2, not to number 3. Right? So in the problem you are considering the story is 3 periodic, and here the story is 2 periodic. So hyperbolic cosine of z is sum z to 2n over 2n factorial n greater equal to 1, greater equal to 0, and hyperbolic cosine, hyperbolic sine is sum n greater or equal to 0, z to 2n plus 1 over 2n plus 1. We know them. We know them from section 1 or chapter 1, whatever. Also, we know that they're expressible via exponential function. So if you look at your exercise, you need to express 3 given functions via exponential function. This is, as we know, e to the z plus, and I'll write it suggestively in the form which will be a hint. Okay? This is probably not very fair, but it's recorded, so it's fair to those who are not here. So I write it suggestively like this: e to psi z, and 1/2 here. And psi is generator in degree 2 roots of 1, also known as -1. So this is the great formula, and the great formula here is 1/2 e to the z plus, you know what I should write next? I already wrote plus. So I should write -1. But for us, -1 is psi. E to psi z. Right? So, keeping this in mind, even not knowing the series, we see from these formulas that let's differentiate. Let's differentiate, and we'll see that cosine of hyperbolic cosine of z prime is e to the z plus e to psi z 1/2 prime. Again, this is 1/2 e to the z plus psi e to psi z. Wow, we discovered that hyperbolic sine is derivative of hyperbolic cosine. Let's do it again. Let's take hyperbolic sine. So this is hyperbolic. Let's do it twice. Then it's 1/2 e to the z plus psi e to psi z prime. And of course, this is 1/2 e to the z plus psi squared e to psi z. Wow, a miracle happened. This thing is equals to 1 because psi is actually -1. So when you put it to the power, which is the order of the roots of 1, so to the power 2, you'll get 1. And this is again hyperbolic cosine. So this should ring the bell, and this should explain a lot about the exercise. Are you starting to get the hint how to write the formulas for alpha, beta, and gamma? So, yeah. Last thing, about it, and then we'll pass to the material we're supposed to cover. Let's see where 1 in the right hand side comes out of. So let's write this, I mean cosine, hyperbolic cosine squared. Minus, and I think this minus is also suggestive. Sine hyperbolic z squared. So this is e to the z plus e to minus z over 2 squared minus e to the z. I will write it shortly. I think that that's enough. Minus e to minus z over 2 squared. So you'll see that, well, each of them, after you open by the binomial formula, each of them will be the product. So this will be 1/4 times 4 times e to the z times e to psi z, which is e to 1 plus psi z, which is e to the 0, which is 1. But remember that in this story, psi equals minus 1. So the right-hand side of the well-known formula that hyperbolic cosine squared minus hyperbolic sine squared equals to 1 comes from this. So, of course, probably for you, you first know about sine squared plus cosine squared equals to 1, and then you pass to hyperbolic ones, and you see that, well, the formula looks similar, only the sign is changed. But you can start backwards. You can start from these ones. And then, of course, you'll get both the formulas for sine and for cosine. Okay. Now, so this altogether should be a hint for, so like a big hint. So for alpha, beta, and gamma, as we know them, psi equals what? Cosine of 2 pi over 3 plus I sine 2 pi over 3. So this is the primitive third root of 1. So this is one hint, and I think that you will, so looking at the formulas at sine and cosine hyperbolic of z and sine hyperbolic of z, just invent the formulas for alpha of z, beta of z, and gamma of z. Of course, you expect that beta is the derivative of alpha and gamma is the derivative of beta, and of course alpha should return. Alpha should be derivative of gamma. So there should be a cycle of derivatives. Like we had cycle of derivatives of degree 2 over there, there should be a cycle of derivatives of degree 3 here. Right, and in view of this, so since expect beta equal alpha prime, gamma equal beta prime, alpha being gamma prime, just invent let's invent alpha of z. In terms of, now you'll tell me which functions I should use. So over there I used e to the z and e to minus z. Here I should probably use something else. Good. So when you do it, you will, I mean, of course you need to compare power series. But if you succeed, you will get alpha of z and then beta of z and gamma of z as well. And the remaining part, so this should cover, well, 1a is about something else, so 1b. As for 1c, yeah, what you really need to do is imitate this proof, imitate this formula. So basically, so for 1c, you need to express 1 as a certain product via powers of alpha, beta, and gamma. So I think this is quite an extensive hint, so you can enjoy it. And are there more questions about the homework?